Imagine this for a second. You've got a common infection, something usually easily treated, but suddenly the medicines just stop working. It sounds like sci-fi, but it's terrifyingly real. It's antimicrobial resistance, or AMR.
It really is a chilling thought, and sadly, it's already a huge global issue. The WHO, the World Health Organization, lists AMR as one of the top 10 global health threats. We're talking about links to almost 5 million deaths worldwide just back in 2019.
And what really gets me is the time factor. The traditional ways we have to figure out if an antibiotic will work, they take, what, 48, even 72 hours? That's ages.
It's an agonizingly long time, especially if you're dealing with someone critically ill or you're in a clinic somewhere without, fancy lab equipment. That delay, it's not just inconvenient, it can be absolutely devastating.
Could literally be life or death.
Exactly. Every single hour counts when you've got a serious infection. Waiting days for those results forces doctors into really tough spots.
Okay, but we're not just here to talk doom and gloom today. There's actually some incredible news, a real glimmer of hope coming out of the Indian Institute of Technology, Madras, IIT Madras.
Ah, yes, some genuinely groundbreaking work.
Right. Researchers there have developed something called the AD device. Now get this. It's a low-cost, chip-based gadget that can spot antibiotic resistance in just 3 hours. 3.
From potentially 3 days down to 3 hours. Well, it's revolutionary. It offers a shortcut to getting the right treatment started fast.
It feels like a total game changer in this global fight. So that's our mission for this deep dive. We're going to unpack this amazing tech, figure out how it works, learn about the people behind it, and really explore what it could mean for healthcare everywhere. Ready to jump in?
Absolutely. Let's get into it.
So before we get to the solution, this AED device, let's just make sure we're all on the same page about AMR itself. It's more than just drugs not working, isn't it?
Oh, definitely. It's actually a fascinating, albeit scary, example of evolution in action. AMR happens when bacteria, these tiny organisms, adapt and change over time. They develop ways to survive the very drugs we designed to kill them.
So they basically outsmart our medicines.
Exactly. Through things like random mutations or sharing resistance genes, they build defenses. This makes our standard treatments, things that used to work reliably, suddenly, useless against these adapted strains. It's a constant battle.
And that brings us back to the time problem. Waiting 2 or 3 days for a traditional test, an AST, you said doctors often can't wait. They start empirical therapy. What does that actually mean in practice?
It essentially means making an educated guess. Based on the symptoms, the likely source of infection, local resistance patterns, maybe, the doctor chooses an antibiotic, often a broad-spectrum one that targets many bacteria types, hoping it's the right one.
So it's a bit of a shot in the dark initially.
Sometimes, yes. And while it can be necessary when time is critical, like in an ICU or maybe a remote clinic with limited options, this practice actually fuels the fire of AMR.
How so?
Well, using broad-spectrum antibiotics when maybe a narrower one would do, or using an antibiotic that the bacteria is already resistant to, it puts pressure on the bacteria. It kills the susceptible ones, but allows any resistant ones to survive and multiply. You're essentially selecting for resistance.
Ah, okay. So the delay forces a strategy that can inadvertently make the overall problem worse. It's a vicious cycle.
Precisely. And it's not just the waiting time. These traditional AST methods, they require quite sophisticated labs, don't they?
Yeah.
Expensive machines, trained technicians.
Which aren't available everywhere, I imagine.
Far from it. Think about rural health centers or clinics in lower resource settings. They often lack the infrastructure, the equipment, the trained staff needed for traditional AST. This creates a huge gap in care.
So people in those areas are even more vulnerable because doctors might have to guess, lacking the tools for a better approach.
That's exactly the reality. It widens the healthcare gap and puts vulnerable populations at even greater risk from resistant infections. And that's where something like this AD device could make such a difference.
Right, let's talk about this device. The AD, it sounds almost too good to be true, fast, cheap, easy. How does this tiny chip actually pull it off? What's the magic inside?
Well, the magic is really clever engineering and science. At its heart is a microfluidic chip. Think of it like a miniature laboratory with tiny channels and chambers designed to handle very small amounts of liquid precisely.
Okay, microfluidics. Tiny labs on chips.
Exactly. And the technique it uses is called electrochemical impedance spectroscopy, or EIS.
EIS. Sounds technical. Can you break that down for us? How does measuring electrical impedance tell you if bacteria are resistant?
Okay, let's simplify. The device uses a special nutrient solution. This solution does two things. It helps the bacteria grow, if they can, but it also makes it easier to measure electrical changes in the liquid.
Okay, like a special soup for the bacteria that also conducts electricity well.
Sort of, yeah. Then you add the bacteria sample and the antibiotic you want to test. Now, if the bacteria are susceptible, the antibiotic kills them or stops them from growing. If they're resistant, they carry on growing and multiplying despite the drug.
And this growth, or lack of it, changes the electricity.
Precisely. As bacteria live and grow, their metabolic processes, consuming nutrients, releasing waste products, changes in their cell membranes, all these things subtly alter the electrical properties, the impedance of the solution around them. The AED device measures these tiny changes in impedance over time.
So it's like listening for the electrical buzz of happy growing bacteria versus the silence of bacteria that have been stopped by the antibiotic.
That's a great way to put it. And the team developed a specific way to analyze these changes, something they call the normalized impedance signal, or NIS.
NIS, what does that do?
The NIS basically translates those subtle electrical fluctuations into a really clear signal. It lets the device clearly distinguish between a sample where bacteria are growing, resistant, and one where they're not susceptible. It gives a clear yes or no answer on resistance.
That's incredibly smart. And the affordability part is just staggering, under $10. How did they manage that? Most high-tech diagnostics aren't cheap.
That's one of the most exciting aspects. They made a conscious choice to avoid expensive materials often used in these kinds of sensors, like gold or silver electrodes. They focused on using cost-effective components without sacrificing sensitivity, thanks to that clever EIS method and the special nutrient broth.
So it's designed from the ground up for affordability and accessibility.
Exactly. That low cost makes it viable for those low resource settings we were talking about, places that desperately need this kind of rapid diagnostic tool.
And you mentioned ease of use, too. Minimal training needed. How simple are we talking? Could a nurse or a technician in a small clinic realistically use this?
That's the goal. The design prioritizes being user-friendly. Obviously, some training is needed. Proper sample handling is always important, understanding how to load the chip, start the test, and read the result, but it's designed to be much, much simpler than running complex traditional lab tests. Think intuitive interface, clear readouts.
So not needing a specialized microbiology degree to run it.
Definitely not. The aim is to empower frontline healthcare workers to get these critical answers quickly.
Fantastic. Let's talk about the people behind this. Who are the innovators at IIT Madras driving this?
The credit goes to a really dedicated team. Key figures are Professor S. Pushpavanam, who's a chair professor in chemical engineering, and Dr. Richa Karmakar, an assistant professor in biotechnology. Their collaboration brought together expertise from different fields.
And what did they say about why it works so well? Professor Pushpavanam, for instance, what was his take on that nutrient solution?
He really emphasized its dual function. He pointed out it's not just about feeding the bacteria, but that the formulation itself enhances the electrical signals they're trying to measure. So it boosts the sensitivity, making it easier to detect those subtle changes caused by bacterial growth or death.
It amplifies the signal, essentially.
In a way, yes. It helps make those tiny changes much clearer and detectable for the EIS system.
And Dr. Karmakar, how does she explain the real-time aspect?
Dr. Karmakar focused on how the device monitors those electrical signals continuously. She explained that by tracking how the signal changes, they can tell if bacteria are multiplying despite the antibiotic that gives one kind of signal change, or if they're being inhibited or killed, which gives a different stable signal. It's this real-time monitoring that allows for such a rapid result.
And this isn't just internal praise, right? You mentioned it was published.
Absolutely. Their findings were published in Nature Scientific Reports in August 2025. That's a highly respected peer-reviewed journal, which adds significant weight to the validity and importance of their research.
Okay, publication in a top journal is great, but lab results are one thing. How did they test it to make sure it actually works reliably? What kind of bugs and drugs did they throw at it?
They did put it through its paces. They used two very common but different types of bacteria, Escherichia coli, E. coli, which you often hear about with UTIs, that's a gram-negative type, and Bacillus subtilis, which is gram-positive.
So covering different bacterial structures.
Right, and they tested these against two common antibiotics that work in different ways. Ampicillin, which messes with the bacterial cell wall, and tetracycline, which stops bacteria from making proteins.
A good range of tests then. And the results?
The results were really impressive. In every combination, the AD device correctly identified whether the bacteria were resistant or susceptible to the antibiotic, and crucially, it did it within that 3-hour time frame.
That's fantastic consistency. But did they try anything closer to a real patient scenario, like not just pure bacteria in a lab dish?
Yes, and this was a really important step. They did an experiment using actual human urine samples. They spiked these samples with E. coli, some resistant to tetracycline, some not.
Okay, simulating a urinary tract infection.
Exactly. And then they tested these urine samples with the ENI device to see if it could detect the tetracycline resistance.
And could it?
It absolutely could. It successfully identified the resistant E. coli strains directly in the urine samples. This showed it has real potential for clinical use, for diagnosing common infections like UTIs quickly and accurately.
That's huge. Moving from the lab bench to something that works with a real clinical sample type. So where does the device stand now? Is it ready for prime time?
It's getting closer. Right now, it's undergoing clinical validation at the hospital right there at IIT Madras. This is super important, testing it with real patient samples, diverse infections, to really confirm its performance in the real world.
Checking its reliability across the board.
Exactly. And the team isn't stopping there. They have plans to commercialize it through a startup company they've formed, Capon Analytics, India Private Limited. The goal is to manufacture it and make it widely available.
Capon Analytics. Okay, so they're serious about getting this out there. Thinking bigger picture now, beyond fixing one patient's infection faster, what does this mean for the global AMR crisis?
The potential impact is massive.
Hmm.
Firstly, by giving doctors fast, accurate information, it helps them choose the right antibiotic the first time. This cuts down dramatically on that empirical therapy, the guesswork.
Less use of broad-spectrum drugs when they aren't needed.
Precisely. Less inappropriate antibiotic use means less pressure driving resistance. It helps preserve the effectiveness of the antibiotics we still have, so it directly tackles the spread of AMR.
And I guess having cheap, easy tests available everywhere could also help track the problem better.
Absolutely. Imagine public health officials being able to get data on resistance patterns, not just from big city hospitals, but from smaller clinics, remote areas, places that are currently blind spots.
Real-time mapping of resistance hotspots.
That's the potential. Widespread AST using a tool like this could give us a much clearer picture of where resistance is emerging and spreading, allowing for targeted interventions. This is vital in places like India, where AMR is a major public health challenge.
It really fits into a pattern, doesn't it? IIT Madras has a history of this kind of socially focused innovation. And Tamil Nadu, the state it's in, seems to be quite a hub for this kind of tech development.
It really does. There's a strong ecosystem there fostering innovation, particularly solutions aimed at solving real-world problems. And this device perfectly answers the WHO's call for new, accessible diagnostic tools to fight AMR.
But it can't be all smooth sailing. You mentioned clinical validation. What are the other big hurdles to getting this device from the IIT Madras Hospital into clinics worldwide?
Well, validation itself is a huge one, proving it works reliably across countless variations in patients and bacteria. Then there's scaling up manufacturing, making millions of these chips consistently and keeping that under $10 price point. That's a major logistical and engineering challenge.
Supply chains, quality control on a massive scale.
Exactly. And distribution, getting it to the remote and resource-poor areas that need it most. Plus, navigating regulatory approvals in different countries, each step requires significant effort and investment.
It's a long road from lab bench to global impact. What's the ultimate vision for the researchers? Are they thinking beyond bacterial resistance?
They definitely are. They see potential to adapt the technology, perhaps detecting resistance in fungi, maybe even looking at viral diagnostics down the line. The core EIS technology might be applicable elsewhere.
Expanding its diagnostic repertoire.
Yes, and also integrating it with digital health systems. Imagine the device instantly uploading results to a secure network, accessible to doctors, epidemiologists, tracking outbreaks. That could be incredibly powerful.
Wow. So this AID device, it really feels like more than just a piece of tech. It's genuinely a symbol of hope, isn't it, in this really daunting fight against AMR?
It truly is. That shift from days of waiting and uncertainty down to just 3 hours, the affordability, the potential to get the right treatment to people quickly, it could save so many lives.
And it's a powerful reminder that groundbreaking science doesn't always need to be astronomically expensive. Sometimes the most transformative ideas are the ones designed to be accessible, to do the most good for the most people.
Well said. It really highlights the power of innovation focused on solving critical global needs.
Absolutely. And as we see innovations like this emerging from places like IIT Madras and Tamil Nadu, it really makes you think, doesn't it? What does this signal about the future of global health innovation? Could the most impactful solutions increasingly come from places closest to the problems themselves? How might that shift redefine how we tackle these huge global challenges? Something definitely worth pondering.